Welcome! In this session, we'll explore an exciting coding challenge, problem number 1161, maximum level sum of a binary tree. Together, we'll break it down step by step and uncover the most efficient way to solve it. Let's dive in. In this problem, you're given the root of a binary tree, and your task is to find the level of the tree that has the maximum sum of node values. The level sum is calculated by adding up all the values of the nodes at each level of the tree. If there are multiple levels with the same maximum sum, you need to return the smallest level number, using 1-based indexing. For the input, we are given a binary tree represented as a root node, and the output is an integer representing the level with the maximum sum. Let's start with an example for better understanding. Here is the first example. The binary tree is visualized like this: the root node has a value of 1, it has two children with values 7 and 0, and the left child of 7 has further children with values 7 and -8. To calculate the level sums, at level 1, we only have the root node with a value of 1, so the sum is 1. At level 2, the nodes are 7 and 0, so the sum is 7. At level 3, the nodes are 7 and -8, and their sum is -1. The maximum sum among these levels is 7, which occurs at level 2. Therefore, the output for this example is 2. In the second example, the binary tree is more balanced. The root node has a value of 1, with children 2 and 3, and each of these nodes has two more children, 4, 5, 6, and 7. Let's calculate the level sums. At level 1, we have only the root node, so the sum is 1. At level 2, the nodes are 2 and 3, and their sum is 5. At level 3, the nodes are 4, 5, 6, and 7, giving us a sum of 22. The maximum level sum here is 22, which is at level 3. So, the output for this example is 3. Now let's consider a simpler example. If the binary tree consists of only a single node with the value 1, the tree has just one level. The sum at this level is simply the value of the root node, which is 1. Since there is only one level, the answer is straightforward: the output is 1. This demonstrates the base case where the tree has the minimum possible size. There are a few important constraints and edge cases to keep in mind. The tree can have anywhere between 1 and 10,000 nodes, and node values can range from -100,000 to 100,000. The algorithm must handle trees with negative node values and correctly identify the level with the least negative sum. Additionally, if multiple levels have the same maximum sum, the algorithm must return the smallest level index in 1-based indexing. These considerations ensure the solution is robust and handles all scenarios effectively. To solve the problem of finding the maximum level sum of a binary tree, the goal is to calculate the sum of node values at each level and determine which level has the maximum sum. This naturally lends itself to a level-by-level traversal, which is typically done using breadth-first search, or BFS. Several approaches were considered for this problem. First, there's the brute force approach, which involves traversing the tree level by level using recursion or depth-first search. For each level, we keep track of the nodes and calculate their sum. However, this method has significant drawbacks, as it requires storing all nodes at each level and involves revisiting nodes multiple times for some calculations. This results in inefficiencies, with a time complexity of O(n) squared, in the worst case, and a space complexity of O(h), where h is the height of the tree. On the other hand, the optimized BFS approach uses a queue to traverse the tree level by level, calculating the sum of node values as we process each level. This strategy is efficient because it avoids redundant operations and processes all nodes of a level in a single traversal. The time complexity here is O(n), since each node is visited exactly once, and the space complexity is O(w), where w is the maximum width of the tree. Lastly, there's the recursive DFS approach, where we use a dictionary to track the sum of nodes at each level. This avoids the need for an explicit BFS queue but introduces additional space requirements for the dictionary. The recursive DFS approach has its own trade-offs. While it eliminates the need for a queue, it still requires space for both the recursion stack and the dictionary used to store sums at each level. The time complexity remains O(n), as each node is visited once, but the space complexity is now O(h), for the recursion stack and O(d), for the dictionary, where d is the depth of the tree. After evaluating these methods, the optimized BFS approach was chosen as the best strategy. This is because it balances efficiency and simplicity, processing the tree level by level in an iterative manner. BFS avoids the need for additional data structures beyond a queue and eliminates redundant calculations, making it straightforward to implement and debug. Comparing BFS to brute force, BFS is clearly faster because it calculates level sums in a single traversal rather than repeatedly visiting nodes. Compared to recursive DFS, BFS is preferable for its iterative nature, which avoids the risk of stack overflow in very deep trees. Additionally, BFS aligns well with the problem's requirements by naturally processing the tree one level at a time. While the BFS approach is efficient and practical, it does come with trade-offs. Specifically, it requires a queue to maintain the nodes at each level, leading to a space complexity of O, W, where W is the maximum width of the tree. For extremely wide trees, this could become a limitation. Recursive DFS, on the other hand, can save space by avoiding the need for a queue, but it introduces the risk of stack overflow for very deep trees. Additionally, the dictionary used in DFS to store level sums also contributes to space usage. In conclusion, the BFS approach strikes the right balance between efficiency, simplicity, and practicality. It avoids the pitfalls of both brute force and recursive DFS by eliminating redundant computations and handling the tree traversal iteratively. For this problem, BFS stands out as the optimal solution, providing a clear and scalable way to determine the maximum level sum of a binary tree. To solve the problem of finding the maximum level sum of a binary tree, our goal is simple: determine which level of the tree has the highest sum of node values. If there's a tie meaning multiple levels have the same sum, we return the smallest level number. To achieve this, the algorithm follows a step-by-step approach. First, we initialize the necessary data structures. A queue is used for level order traversal, which ensures we process all nodes level by level. We also define variables to track the current level number, the maximum sum found so far, and the level where this maximum occurs. Once these structures are ready, we start with a breadth-first search traversal of the tree. The root node is added to the queue, along with its level, which is level 1. From there, we process the tree level by level, ensuring each level's nodes are handled completely before moving to the next one. At the start of processing a level, we initialize a variable called level_sum to accumulate the values of all nodes at that level. Then, for each node in the current level, we dequeue it from the front of the queue and add its value to level_sum. If the node has left or right children, we enqueue them for processing in the next level. After all nodes at the current level are processed, we compare the level_sum with the current max_sum. If level_sum is greater, we update max_sum and record the current level as max_level. Once this comparison is complete, we increment the current _level counter and move on to the next level. This process continues until the queue becomes empty, meaning all levels of the tree have been processed. Finally, after traversing the entire tree, the algorithm returns the value of max_level, which is the level with the highest sum. The breadth-first search, or BFS, is the core traversal technique used here. It's a natural fit for level order traversal because it systematically processes all nodes level by level. This ensures we can compute the sum for each level without missing any nodes. The queue is the data structure that enables this traversal by maintaining the order of nodes to be processed. By enqueuing children as we process their parent nodes, we ensure each level is handled in sequence. To update the maximum sum, we compare the sum of the current level, level_sum, with the running maximum, max_sum. If the new sum is greater, we update both max_sum and max_level. Importantly, ties are resolved inherently by the level order traversal since levels are processed in increasing order. Beyond the queue, we also use variables like max_sum, max_level, and current_level to keep track of the traversal state and results. Now let's analyze the key operations and their complexities. The enqueue and dequeue operations for the queue are both O(1), and since each node is enqueued and dequeued exactly once, the overall traversal time is O(n), where n is the total number of nodes in the tree. For space complexity, the queue will store nodes at the largest level of the tree. In the worst case, such as a fully balanced binary tree, this requires O(w) space, where W is the maximum width of the tree. The algorithm is robust against edge cases. For example, in a tree with a single node, the level sum is simply the value of that node, and the level is 1. If the tree contains negative values, the algorithm still works because it directly compares sums, regardless of their sign. Additionally, if multiple levels have the same maximum sum, the smallest level number is returned due to the natural order of level processing. The pseudocode provides a step-by-step implementation of these ideas. The pseudocode begins by initializing a queue with the root node and its level. We also set up variables for the maximum sum, the level associated with it, and the current level. The traversal proceeds as long as the queue is not empty. At each level, we calculate the size of the queue, which represents the number of nodes at that level, and initialize a level_sum to 0. For every node at the current level, we dequeue it, add its value to level_sum, and enqueue its children, if they exist, to ensure the next level is processed. After processing all nodes at the current level, we check if level_sum exceeds max_sum. If so, we update max_sum and set max_level to the current level. Finally, we increment the current_level counter and repeat this process until all nodes are processed. The function concludes by returning max_level, which represents the level with the highest sum. There are a few optimizations we can consider to improve the algorithm. One is an early exit strategy. If the sum of a level exceeds the maximum possible sum from the remaining nodes, we can terminate the traversal early. This could save computation in certain cases. For space optimization, we can use 2 queues, or even a marker, to reduce memory usage when processing levels. By carefully managing these resources, we can make the algorithm more efficient without changing its correctness or results. The given code solves the problem of finding the level in a binary tree with the maximum sum of node values. Here's the breakdown. 1. Input validation *. The function first checks if the root is none. If so, it returns 0, as there are no levels to process. 2. Initialization *. A queue is used for level order traversal, where each element is a tuple of a tree node and its level. A default dict is used to store the cumulative sum of node values for each level. 3. Level order traversal *. The while loop processes nodes level by level. For each node, its value is added to the current level's sum in level_sums. If the node has left or right children, they are added to the queue with their respective levels, current level plus 1. For finding the maximum level sum * after the traversal, the code calculates the maximum sum across all levels using max level_sums.values. It then identifies the smallest level that achieves this maximum sum using a generator expression with min. This approach ensures an efficient solution with a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited once. The space complexity is O(h), where h is the height of the tree, due to the queue used for traversal. The solution handles edge cases like empty trees, single-node trees, and trees with multiple levels having the same maximum sum. Here, we begin by importing the necessary Java utilities and defining the treenode class, which represents the structure of each node in the binary tree. The treenode class includes fields for the node's value, as well as references to its left and right child nodes. We also define a constructor for the treenode class to initialize these fields. Next, we move to the solution class, where the maxLevelSum method is implemented. This method aims to find the level of the binary tree that has the maximum sum of node values. To start, we handle the edge case where the root is null by returning 0, as there are no levels in an empty tree. We then initialize a queue to facilitate a level order traversal of the tree and add the root node to it. 3 variables are declared: level to keep track of the current level during traversal, max level to store the level with the highest sum, and max sum, initialized to the smallest possible integer value, to track the maximum level sum encountered so far. The method proceeds with a while loop that continues as long as the queue is not empty, ensuring all levels are processed. At the start of each iteration, we determine the number of nodes at the current level using queue.size, and initialize current level sum to 0. A for loop then iterates through all nodes at this level. For each node, we remove it from the queue, add its value to current level sum, and enqueue its left and right children if they exist. After processing all nodes at the current level, we compare current level sum with max sum. If the current level sum is greater, we update max sum and set max level to the current level. Finally, we increment the level variable to move to the next level. Once the queue is empty and all levels have been processed, the method returns maxLevel, which holds the level with the maximum sum. To solve this problem, we process the binary tree level by level, calculating the sum of node values at each level. For this example, we start with the given binary tree. The root node has a value of 1, and its two children are 7 and 0. The left child of node 7 is another 7, and the right child is -8. First, we initialize a queue with the root node and its level, which is 1, and a dictionary called level_sums to store the sum of values for each level. At level 1, we dequeue the root node, which has a value of 1, and add it to the sum for level 1. This makes level_sums equal to 1, 1. Then, we enqueue its children, nodes 7 and 0, along with their level, which is 2. Next, we process level 2. We start by dequeuing the node with a value of 7, adding its value to the sum for level 2. Now, level_sums becomes 1, 1, 2, 7. We enqueue its children, node 7 and -8, at level 3. Then, we dequeue the node with a value of 0, but since 0 doesn't change the sum, level_sums remains 1, 1, 2, 7. For level 3, we dequeue the node with a value of 7 and add it to the sum for level 3, updating level_sums to 1, 1, 2, 7, 3, 7. Next, we process the node with a value of -8, adding it to the sum for level 3, which results in level_sums being 1, 1, 2, 7, 3, -1. Finally, we look for the maximum sum across all levels. The highest sum is 7 at level 2, so the output is 2. Now, let's explore a balanced binary tree example. The root node, 1, has two children, 2 and 3. Each of these children has two children of their own, nodes 4, 5, 6, and 7 at level 3. First, we initialize our queue with the root node and its level, and an empty level_sums dictionary. At level 1, we dequeue the root node, add its value to the sum for level 1, and enqueue its children, nodes 2 and 3, at level 2. Next, at level 2, we process node 2 by adding its value to level_sums and enqueuing its children, nodes 4 and 5, at level 3. Then, we process node 3, add its value to the sum for level 2, and enqueue its children, nodes 6 and 7, at level 3. At this point, level_sums is 1, 1, 2, 5. For level 3, we process all 4 nodes, 4, 5, 6, and 7, we add their values to the sum for level 3, which updates level_sums to 1, 1, 2, 5, 322. Finally, we identify the level with the maximum sum. In this case, the highest sum is 22 at level 3, so the output is 3. This example demonstrates how the algorithm efficiently calculates the sum for each level, even in a balanced binary tree. Finally, consider a simple example with a single node tree. Here, the tree consists of only one node with a value of 5, which is also the root. We initialize the queue with this root node and its level, and level_sums as an empty dictionary. At level 1, we dequeue the root node, add its value to the sum for level 1, and update level_sums to 1, 5. Since there are no other nodes to process, we directly find the maximum sum. The highest sum is 5 at level 1, so the output is 1. This example highlights how the algorithm handles edge cases like a single node tree effectively. To analyze the time complexity of the algorithm, we start with the level order traversal. This traversal visits each node in the binary tree exactly once. If the total number of nodes is denoted by n, the operations performed for each node, like dequeuing it, updating the corresponding level sum, and enqueuing its children, each take constant time, or O1. Since these steps are repeated for all n nodes, the overall cost of the traversal is O(n). Once the traversal is complete, the algorithm uses the level_sums dictionary to store the sum of values at each level. If the tree has h levels, iterating through this dictionary to find the maximum level sum takes O(h) time. Additionally, determining the smallest level with that maximum sum involves another pass through these h levels, which is also O(h). Together, these steps give us the time complexity for this part of the algorithm. Now, considering the height of the tree, h can range from O log n for a balanced binary tree to O(n) for a skew tree. However, the dominant factor in the algorithm remains the level order traversal, which processes all n nodes. This makes the overall time complexity of the algorithm O(n). Next, let's analyze the space complexity. The first component is the queue used for level order traversal. The queue holds nodes during the traversal, and its maximum size occurs at the widest level of the tree. For a balanced tree, the maximum width is roughly the number of nodes in the last level, which is approximately n/2. In a skewed tree, the queue holds at most one node at a time. Therefore, the space required for the queue in the worst case is O(n). The second component is the level_sums dictionary. This dictionary stores one entry per level, with the number of levels being h. For a balanced tree, h is O log n, while for a skewed tree, h is O(n). Hence, the space required for the dictionary is O(h). When we combine these components, the overall space complexity of the algorithm is O(n) in the worst case, such as when the binary tree is skewed. For a balanced binary tree, the queue remains the dominant factor, leading to a space complexity of O(n) as well. Let's compare this with a brute force approach. In a naive solution, you might traverse the tree multiple times, once for each level, to calculate the sum of values at that level. If the tree has h levels and n nodes, this would result in a time complexity of O(h*n) in the worst case. The proposed algorithm, however, achieves the same goal in a single traversal of the tree, reducing the time complexity to O(n), a significant improvement over the brute force method. Finally, let's validate the big O analysis mathematically. For time complexity, each node is processed exactly once, involving O(1) operations per node. With n nodes, this totals to O(n). Additionally, iterating through the level_sums dictionary involves O(h) operations, where h is the number of levels. Since h is always less than or equal to n, the overall time complexity is dominated by O(n). For space complexity, the queue used in level order traversal holds at most O(n) nodes in the worst case, while the dictionary stores O(h) entries. Again, since h is at most n, the total space complexity remains O(n). This analysis confirms that the algorithm is both time and space efficient, offering significant improvements over brute force approaches by minimizing redundant computations and memory usage. One common mistake when solving this problem is confusing level order traversal with depth first search, or DFS. While DFS is a valid tree traversal method, it doesn't process nodes level by level, which makes it unsuitable for calculating level sums without additional bookkeeping. Instead, breadth first search, or BFS, is the correct choice because it processes nodes one level at a time, ensuring accurate level-to-sum mapping. Another frequent error is forgetting to return the smallest level when multiple levels have the same maximum sum. To avoid this, always track both the maximum sum and the smallest level index during your traversal. Additionally, space management is critical. Storing all nodes for each level in separate data structures can quickly lead to high memory usage, especially in large trees. A better approach is to process nodes directly within the BFS queue to minimize overhead. Edge cases, like empty trees or single-node trees, are easy to overlook but can cause runtime errors if not handled explicitly. Lastly, watch out for integer overflow when summing large node values. Use data types that can accommodate large sums or consider modular arithmetic to handle these scenarios safely. This problem is designed to test your ability to implement level order traversal using BFS while efficiently managing auxiliary information, such as level sums. The optimal solution achieves a time complexity of O(n), where n is the total number of nodes, since every node is processed exactly once. The space complexity, on the other hand, depends on the maximum width of the tree, denoted as W, making it O(w). Recognizing patterns is another key takeaway here. Many tree-related problems, such as finding the maximum depth or calculating averages at each level, rely on similar BFS techniques. Mastering these patterns will significantly improve your problem-solving speed and adaptability. Additionally, interviewers may explore follow-up questions, such as asking for the average of the maximum level sum instead of the sum itself, or even challenging you to solve the problem using DFS rather than BFS. Being prepared for these variations demonstrates a deeper understanding of the problem and its underlying concepts. To deepen your understanding of this topic, consider exploring related problems. For example, in binary tree level order traversal, LeetCode 102, you'll practice the foundational BFS technique used to traverse trees level by level. Another great problem is average of levels in binary tree, LeetCode 637, which is similar to this one but focuses on calculating averages instead of sums. You can also try find largest value in each tree row, LeetCode 515, where you identify the largest value at each level, and maximum width of binary tree, LeetCode 662, which involves determining the widest level of the tree. Now, if you're looking for alternative approaches, you can solve this problem with DFS by passing the current level as a parameter and maintaining a dictionary to store cumulative sums for each level. This method achieves the same time complexity but requires careful handling of recursive calls. Another variation is using a single queue with a marker, such as none, to distinguish between levels instead of managing two separate queues. While this reduces overhead, it demands careful implementation. In terms of trade-offs, BFS is generally easier to implement and debug, making it ideal for level-based problems, though it might use slightly more memory. DFS, on the other hand, can be more memory efficient for extremely wide trees but tends to be harder to implement without introducing bugs. Great job! Today, we tackled the problem maximum level sum of a binary tree and learned how to efficiently compute and analyze tree structures. Remember to practice similar problems to refine your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!